Okay, let's discuss parametric equations here for a second. So there's a couple cool things about parametric equations. One is that it gives you kind of direction, which is different than the typical XY coordinate plane graphing, right? Functions. You can actually get a direction in here. And a second thing that's kind of cool is that parametric equations or parametric function can allow you to be able to represent things that don't pass the vertical line test, because a lot of times in real life things come back and forth on each other. So we'll see that right now. Let's do this first one. This is the first type, the one that gives you kind of a direction of what's going on. So just like any kind of graph, if we have no idea what to do, we might decide to make a t-table, although this one will technically be a double t-table. So I'll make a t and an x and a y, and our t is supposed to start at the value of -3. And if I plug in -3, you can see that you're getting, let's see, if I plug in -3 for the t value into x, -3 squared is 9, 9 plus 1 is 10. And then if I plug in -3 for the y, I get -3 minus 5, which is -8. So at time equals -3, this particle or bug or whatever is at the spot 10 comma -8. Now at -2 squared is 4, 4 plus 1 is 5, so the x coordinate is going to be a 5, and the y coordinate, -2 minus 5 is -7. Okay, we can start plugging in more and more numbers, but you'll see that, like, well, this is a parabola, right? X equals t squared plus 1, so something kind of interesting happens at 0. Let's plug 0 in next. Let's see, 0 squared plus 1 is 1, so that gets to 1. And then when I plug in the 0 for the y, I end up getting -5. And then what's going to happen to these x values is these x values are going to kind of sort of go back up on each other. So 1, 2, 3 are going to go back out like the 2 and the 3 here. So I'm going to now jump out to 3 and see if this gives me enough information. 3 squared plus 1, 9 plus 1 gives me a 10. But the y coordinate is now different, right? 3 minus 5 is -2. So what is this particle doing with position of starting and directional movement is that it looks like I need to have x coordinates that vary from about 1 to 10, so I'm going to be over in this area, and my y coordinates go down to -8 and up to -2. So I'll count by 2's, I think. -2, -4, -6, and -8. And then along the x-axis, let's also count by 2's because I got to get out to 10. So I'll go 2, 4, 6, 8, 10. And essentially what's happening here now is at time equals -3, or t equals -3, sorry, the parameter, x is 10, y is -8, so I'm kind of located down there. That's at time equals -3. Then as time moves on to -2, I move to 5, -7, so I'm going to move in here a bit, and my y is going to be -7, so that's what happens at time equals -2. -1 is going to presumably kind of continue this path, but so far I have it kind of moving like this. And then I skip -1 just to get more points in there, make it a little bit more efficient for the video. But if I plug in 0, then I need to be at the point 1 comma -5. So x equals 1, y equals -5 means you're going to be up here. And presumably somewhere in the middle here is where time equals -1 happens. But then it's going to turn back on the directions. The x's start going from 1 to 10, and the y's still continue to move upward towards -2, ending at 10 comma -2. So 10, -2 is right there. Again, sorry, this was at time equals -2. This was at time equals 0. And then it warps back around like that, and that's where it stops at time equals 3, because we only went from between -3 and 3. So we're getting a sideways parabola, but we start at a particular point and we end at a different point. Okay, so hopefully this makes more sense about what's going on with the parametric equations. Let's do one more quick example since we have this up here. Let me turn on this layer. That layer kind of overlaps. So never mind, we'll do that layer later. I'll do one with a graph that is, actually this graph is not a function either, so we actually get the directional part and the not a function part. Pretty cool, actually.